Okay. Condition monitoring. As you can see from this nice picture, what would be the topics we consider here? I will skip my introduction before because I have done this already. For those who are joined later, could look into this. I'll do a brief overview where we started, what we did there, and give some more details. And beside that, beyond this condition monitoring, we designed for 417. There are additional CANopen connectivity and technologies which could, additionally to condition monitoring, give you an opportunity to communicate your data, even those of condition monitoring, into the cloud services, whatever, to give it to the end customers. And finally, we talk about system design, constraints, and opportunities coming with our additional protocols and functions which are designed beyond this 417 condition monitoring. So we start from there. When we did this for a couple of years back with additional task force, so we organizing this, as my colleague already told at the beginning, we have technical groups. CANopen Lift is a special interest group. Within this group, we organize the task force to handle the condition monitoring, to specify the condition monitoring. There are specific people who working exactly on this one in the companies joined us, and we designed it. And our first thought was, what should we do? Actually, condition monitoring, Internet of Things, in reference to the Internet of Things, cloud services, internet gateways, and this infrastructure becomes somewhat advanced nowadays, and the data from embedded networking will be collected also in a sophisticated way. So we thought, actually, in the first place, we provide the data itself in CANopen networks and give this data forward on to some specific device or entities which submitted for the further processing on the way to the remote monitoring. So we thought, shall we do this our own, some kind of data specification? And we knew about efforts of VDMA regarding condition monitoring. We suggested to use this way rather than do one very specific. So that is the standardized one. So we chose VDMA specification on this topic to work on and design our condition monitoring approach based on it. Additionally, IEC 81346 specifies standardized identification of functionalities providing this kind of monitoring, whatever prediction maintenance, but it was optional in this case. So we go with the standardized ways, and so what we can take from VDMA 24582 specification, let's say, into our CANopen Lift condition monitoring. So requirements came first, of course, and we looked into what we want to do, what we want to have. Basically, as my colleague and me said at the very beginning, CANopen is actually providing only short messages, 8-byte long, and very effective way. However, this means we couldn't push the data a long way on it, like the total process data from or every data from the CAN network into the CAN bus. It will be overload actually our communication. So we said we would like to have a limited number of monitored parameters for now, for the moment. And these parameters could be monitored should be capable, every lift component should be able to use the very same parameters to provide the status of their current disposition. So what's the requirement we would try to reach? And the means for this requirement were the VDMA specification, which is not actually released, but even the work draft gave us certain opportunities to look into. And so we tried to design that. This was actually the architecture of condition monitoring. How should it be done in all kind of field bus system? So this VDMA specification was not meant to be only for the very limited number of field bus, but for any field bus or general condition monitoring in embedded systems in general. So it could help us and give us an opportunity to have design these devices standardized way. Additionally, CAN Automation designed its own IoT-related, cloud-related, data-related, standardized data-related stuff for submitting the data through the cloud services into the technician in the field, using identification of the functionality, using standardized CANopen to TCP/IP gateway, and the protocols in there, and the web service we could have used whenever we need it, like RESTful HTTP, WebSocket, MQTT. So I could arrange a completely transparent TCP/IP and HTTP web servers in there and web clients, and communicate the data through it. The representation of the data and the system structure monitoring could be done in standardized way. Either we submitted data over the HTTP in XML or JSON-based one in multiple user languages. Additionally, it is possible that a technician in whatever country, whatever language he speaks, or he or she speaks, you will have this interface and access the data without knowing and having a knowledge of CANopen itself, which would be deeply embedded into this programming interface. The user, the technician, would just know which function in general, system independent, field bus independent, he would like to fix or maintain. So then we come up with this both things, and how did we fit them into our specification, into our condition monitoring concept. So the first thing was in there to have it in a structure. VDMA provided opportunity to provide the architecture of the whole condition monitoring system with all predictive maintenance and preventive measures, whatever it might be. It's structured in a certain way. So there is a function environment, application environment, and automation environment. So in function environment, I do know I have to define functionality I need to use to monitor whatever it might be. In application layer or environment, I know where this function I've designed before or I would monitor before set, in which real component it is related and which component should monitor this function. So from this point of view. And another, this virtual structure, the automation layer, I know where this function and a component is located, where it is exactly located in which physical component in there. So, and then we had to apply this concept into CANopen parameter and in CANopen communication structure. How do we transmit this data? Which data do we specify? What is behind these functionalities? So the first one was to define where the functions are and how do we handle them. You see now the table, we talk about function layer, and the functions would be, for example, in its classification, for example, number of trips the lift car does, to indicate how this may be deteriorating over the time, and or providing the general information, how many trips it is done. You could compare then with it information about the lift itself, how long can it go on, the hour meter, number of hours the lift operated, the motor temperature, the trip quality. There are only few of the about 30 and 40 parameters we can monitor as the functions. Another one would be deeply restructuring this functionality based on the kind of the attention we would take on them. Either we monitor them or do preventive maintenance or predictive maintenance. As you can see, there's preventive or monitoring is just monitoring the system and see and inform the technician what is the time to replace the component or take attention or fix some specific malfunctions in there. There is also predictive maintenance where we know is there a possibility that the system completely deteriorates in there. And the next slide, and this slide actually, you can see more details, the total overall structure we had taken and adopted from VDMA into our CANopen Lift condition monitoring concept. So we have input parameters which we are handling in there, which we have to evaluate and which would lead us to give an overview what is going then in the very specific component. Maybe some input data additional and so on. The parameter for actual value monitoring, which we really monitor, will be coming also inside. The upper lower thresholds and reference values will be actually the limits for these values we have to monitor as well to know what is going on there. There is also interesting to know the state of this total system or this single component. As I said, we could monitor not only the system itself, but very single component, and each component would provide this data over the bus to the monitoring station or whatever. But we'll come to this point later. So now we go on this various input parameters or details we need to know to make condition monitoring itself effective on the way. There is also this identification we described before, condition monitoring, the function identification, the structuring of this one comes an input in this green box, which is actually not the black box. This is the structure, internal processing of our values in there. There is also a mode of maintenance with which we looked in there before, what kind of maintenance is done there. Is it just simple monitoring or timely preventive maintenance, predictive maintenance, whatever it might be. And the output, in output, I give the value in output of my monitored parameter. I give the traffic light way to know what is going on in basically with parameter itself, with green, red, yellow, or gray, the state of the device, the component, does it require maintenance or not? And then finally, we have also the status output. What is the current status of my system, my current component, or the state of, and the state of maintenance as well. Is it still monitored or is already finished the monitoring? So beside that, we go another pieces we have not discussed yet is component structure and automation layer. So just to give you an overview how VDMA-based structure fits into 417, what we have thought about this. The function in this case is not the monitored function itself, but the component where the function is actually located. I've took the previous example. So we have lift trip counter. It is located and referred to host controller. How meter is also the host controller. And above you can see the hierarchically organized piece of equipment which is related to each other. Where could I get this value itself, how they're related to this functionality I would like to monitor. And finally, we have the automation layer where we define where the functionality I actually monitor is physically located. As in this example, lift trip count and hour meter are located in lift controller. They could also be located in other parts, but for example, as we said, we have limited number of data, or not limited, but a small number of data, and it should be reused. For example, motor temperature and some advanced parameter, which I have not listed there, could be reused by inverter, or not reused, but used by inverter, or at the same time, the door controller can be used, or door unit can be used for its motors, can be using this motor temperature, deliver it to the participants who would evaluate these values, for example. So the maintenance strategy and access of data is occurring in this case. The process monitoring, however, is such a bigger thing. It would, to a certain point, allowed to do in CANopen network, but sometime would overcome this capabilities. So for a limited number of process data monitoring, it will be possible, but we would like to limit our data to the condition monitoring. So how it is done, actually, we have advantage in CANopen Lift for this. So we have basically defined 10 parameters, about 10 parameters for condition monitoring data, including the status, monitoring maintenance modes, how we do the stuff, output parameters, which we actually monitor, the limits we monitor, input data, traffic lights, indication, everything is put in about these 10 CANopen parameters only. However, the communication occurs by each single device using its own manufacturer-specific multiplex PDO. As I said previously, could transmit 254 data pieces, each maximum 32 bits. But for limited number of bytes, we have a limited number of parameters, we have about 30-40 monitored parameters. That were quite useful. Each component might be using 3 or 5, maybe 10 parameters to transmit using MPDO to this end monitoring station. We will talk in the next slides. Basically, the status of the monitoring provides literally all the information you need to know what is going there and what you have to do, and what, for example, the technician as it goes receives this data in his laptop or tablet rather, sees what is going right now with the device, with a component, lift component, and can handle accordingly. So now you can see the nice pictures of it. This is overview of this network, of a simple network, lift network, consisting of one lift network, where we do have this condition monitoring. There are 3 stations in there which could perform condition monitoring. So we have designed into there several optional features. If you do condition monitoring, basically it could be done by host controller, which you see in the middle of this one. You can collect all this data, collect the data, and not only collect the data, each single device transmits via MPDO, using MPDO, this data, and a host controller receives it. Host controller, a lift controller, could have limited capabilities, although they are grown say each time over the course of years, they've grown more resourceful whatsoever, but still we have CAN bars, so we had to take care of communication traffic. So we have to limit this, or maybe not limit this, but for now, for host controller, we have maximum about 40 parameters to receive into. This one opportunity can be used to get the data. Additionally, our member requested that we have independent unit that could collect all the data transmitted over the bus, maybe even from some components which produce more data in there, but this could be collecting. This unit is called condition monitoring, could be designed with whatever you have in there. And it could be having also straight communication to the cloud services using infrastructure, which we do not care for now, but it will be a manufacturer-specific one. On the other hand, the same information could be collected, as my colleague said, with this gateway, which is usually located in the lift network. But this gateway might have a 309 standardized structure in there with our CANopen IoT features, allowing to collect this data and push it into the cloud services in a very predefined way, even transparently. So as you see, there are 3 opportunities how to do condition monitoring in a lift. This one is what you can do. The next slides I would like to attend you even in short. They are optional opportunities, go beyond the 417 standardized capabilities we discussed previously. I would cover our optional CANopen IoT services and data and so on. This is in general structure of the communication path into the cloud, into end user, which will be a technician or remote monitoring station. We have down-layered CANopen network, lift network, or whatever network it could be. It applies to every CANopen system and application which would use CANopen IoT. So we have a cloud connectivity specifications for that reason, which you could use for cloud connectivity in this way. They are not a part of 417, but you could use it for CANopen in general. They could be actually part 417 if you want to do this. So they're not restricted in there. We have also security and future technologies available also for this reason. It's coming very soon. The block diagram of the total IoT structure, CANopen IoT structure, we've designed this optionally independent from 417, just for every CANopen device we could reuse. We have RESTful HTTP server, and we could have a process image and submit data in a very predefined way using a simple gateway into the edge gateway and there into the cloud services. Our 309 standardized gateway for all purposes, for CANopen devices, whatever CANopen networks, has now also user and resources management. You're welcome to look into this specification as well. And finally, how do I do system design using also integrated and even about optional functionality designed in CANopen in 309 specifications. I have physical addressing of my network. And how do I do from the beginning, design my network, design my devices to make them already fit for a unified system and field bus independent systems, where you don't need actually to have on a higher hierarchical level even the knowledge of CANopen. One is where it is still required is CANopen physical addressing. I address always devices by the physical CANopen identification, CAN ID, the device node IDs, and so on. The standard I mentioned at the very beginning, in combination with VDMA profile, provides the identification of functionality we can use with unique reference designator, which defines the very single functionality, the very uniquely functionality available in the system, but CANopen and other technology independent. So the technician could see this functionality as literally as a light generation, as in this example, unit, for example, indicating in elevator, in a lift, at a very specific building floor and lift, can see this light on in his laptop, but the data, the CANopen information is actually hidden from him. This information, the CANopen, should be designed in embedded network and programmed by CANopen technician who knows about this. But the other technician who has no knowledge of CANopen could simply using this with this standardized approach. The device commissioning of each single device component, we have a DCF file for this case, and a device description would be looking exactly like this, with this parameter reference designator, where I know exactly about each single parameter where this is located from the system point of view. Sorry. Back to this one. Yeah, this is standardized structure of CANopen. It is, and rather device configuration file. This red marked entries coming with this optional standardized IC identification. If you design your lift component, for example, already with those one, so you could have your independent system-wide identification in there. Now, just independently from that one, we design in CANopen 417. It's just in addition to this. So, well, this is so far about optional means we could use along with 417 or just in CANopen general system design. We have certain activities going on there with OPC UA as well. The things about CANopen IoT are actually ready and available. You could use them. You could have these RESTful web servers with RESTful HTTP WebSocket communication to or from CANopen network and pushing this back to this transparent way through the gateway into web server whenever it might be. We have this logical addressing I talked about before. We have a certain possibility using a node list, which I would ask you if you want to know more, look into 309-5 specification more exactly. Node list, the point of view of my system concerning its topology, where the device is topologically located in there. So it will be helpful, and it gives the node list the information about this there. So, and 4.17 condition monitoring is ready. About 1 year back, we have released this. About at the beginning of this year, I think we released it, and ever since it is already designed more or less. We could check out in upcoming Plugfest once it is possible. We could see the first results of it. So summarizing this all stuff, all the things available for you if you're starting with this one, starting with the lift in general. You know that we're offering now condition monitoring, and actually we're thinking about to offer condition monitoring for every CANopen based devices in there, not only for lift, but especially for lift, it is done in predefined way. Additional means how to do so using TCP/IP services is also specified and is available from Canyon Automation. However, only for our members. This is so far from my side for lift condition monitoring and beyond to this topic.